Yeah.
My name is Daniel Watkins. I'm going to give a brief introduction to graph theory, which is an area of math that has a lot of interesting real-world applications. It allows us to understand systems in the real world. So I'm going to start with an abstract explanation of just what graph theory is, and then go into the concrete examples. So a graph, it's not one of these XY plots that we're talking about. This is actually a set of two sets. One that we'll call V for vertices, and another set E of edges. So you can have vertices named whatever you like. Let's say that V is equal to A, B, C, and D. It could also be 1, 2, and 3, or they could be Bob, Pete, and Sue. That's not completely random, as you'll see in a second. Edges are simply pairs of vertices. So we'll make a graph that has these pairs. And the reason for the name graph is because this can be best understood if we represent it graphically. So I'll write out these vertices, A, B, C, and D. And then the set E consists of connections between these points. So we have A to B, B to C, C to D, and A to D. Now, of course, this can have a lot more than 4 vertices. You can have very large graphs. You can have small graphs of all sorts of shapes and sizes. There are some questions that we can ask to try to understand any graph a little bit better. I'm going to come over here and make a table, and we'll apply this to some real-world networks. So some questions that we could ask are which of the vertices or which of the edges is most important? So I'll say VE importance. Some measures of this are called betweenness, and say how many of the edges go through a specific point. On this example, all of the points have an equal number of edges going through them. But if we were to add another vertex right there, we would have say that's E. And then instead of A to D, we would have A to E, E to D, C to E, and B to E. All of a sudden we have one point that is a lot more important than the other ones. The graph would fall apart if I removed those edges, whereas if I removed one of these, less would happen. So the questions that we can ask, the importance of specific vertices and edges. We can also look for clusters, and we can look for shortest paths. So a cluster will be apparent in some of the networks that I mentioned, but if I draw another example graph that looks like, say, this with vertices at each of the crossings, you've got one full graph, but you've got these smaller sets of connected pieces, and these would be what I would call clusters in the graph. So the question for you, before we go further, what are some examples of networks that you see in the real world? Any ideas?
Internet.
Where do you see networks?
Hierarchical structures.
Okay, so like an org chart for an organization. Yes, that is a good one. I'm going to just abbreviate that word because I don't know how to spell it. So Facebook, or more in general, I'm just going to put social networks because they don't have to be online, but we would have connections of people.
That's street maps, I guess?
Yes. Okay. So I'm going to actually put these over here because those are some that I was intending on looking at. So we have streets, we have social networks. Another one, I'll throw out a couple more examples. When you're looking at cell biology, you have thousands of different proteins going on, and they interact with each other in complex ways. You can represent proteins as the vertices and have the chemical interactions as edges. Kind of under the topic of social networks, you could be looking at the vertices being businessmen and the connections being serving on the same board of directors. And you can kind of see which companies are more connected to each other than others. If you're in the defense industry, you could be looking at terrorist networks to try to find communities of adversaries working together. So looking at these questions that you can ask about a basic graph, so the betweenness, the importance of vertices and edges. For streets, you could look at which roads and intersections are the most important. Which ones could you do construction on without any trouble with detours, and which ones would mess everything up if you closed it? So in this area, if you closed the entire Ben Franklin Bridge, that would disrupt a lot of traffic patterns. But if you were to just block one of the small streets in University City, most people's traffic wouldn't be disrupted. In a social network, you could be looking for the people that are have the most friends, the people that are the most influential. Advertisers would want to know which people give the most influence. You get them wearing your t-shirt, and their friends might wear it too. So, so you have influence. Another application that some of the national labs are working on is epidemiology. When there's the scares about the bird flu or different viruses, you want to know how it's going to spread, how fast it's going to spread. And if you make a graph model with people as the vertices and day-to-day interactions as the edges, then you can simulate how a virus might spread through that network. So I'll put that down here. And then for proteins, you could be looking at diseases. Some genetic diseases cause malfunctions in the way that a protein is made. If some proteins are more important than others. If you have one that, like say you have this one protein that interacts with all of these other ones, and that one gets malformed, then you could end up with catastrophic effects through the whole system. So, so if you want to look at the effect of defects, if you're looking at clusters, it'd be an interesting problem to try to identify small neighborhoods from an entire road network. In a social scene, you could be looking for groups of friends. You could be looking for sets of proteins that work together a lot. And then one that's especially of interest is for the streets is shortest paths, because you want to know the quickest way to get there. But because not all roads are created equally, one thing that you can do is attach weights to each of the edges. Maybe this edge is 35 miles an hour and 10 miles long. And this one is 10 miles an hour and 8 miles long. This one might be longer, but you'll get there quicker. So, so your GPS would use that a lot. The epidemiology thing could come in here too. The influence thing could come in here. So just in summary, graph theory is an area of mathematics that has a lot of very useful connections to other areas of science. It's been getting a lot of attention recently. In the last 10 years, there's been a ton of papers written on these applications. And it allows you to recognize patterns in very complex systems in a very efficient way.